this video, we discussed learning outcome number 3 from lesson 4.2, which is all about disjoint or mutually exclusive events and the consequences for the addition rule when two events are mutually exclusive. So here's the definition. We say that two events A and B are disjoint or mutually exclusive if they cannot occur at the same time. In other words, if you look at the Venn diagram for events A and B, there is no overlap in disjoint events. So here are a couple of Venn diagrams. Now this Venn diagram on the left shows two events that are not disjoint. So maybe all of the ways that event A can occur are in this pink circle, and all of the ways that event B can occur are in this circle. If there are any ways in which event A and event B are occurring at the same time, they would be listed in this overlapping section. So if those two circles overlap at all, then the events A and B are not disjoint. Now, if there is no overlap, if all of the ways that event A can occur are in this circle and all of the ways that event B can occur are in this circle, we say there's no overlap, they have nothing in common, except for the fact that they belong to the same universe. And those are disjoint events in this case on the right. So let's look at some examples. In these examples, we're going to try to determine whether events are disjoint, or we might say whether events are mutually exclusive. Remember, those are two different ways of saying exactly the same thing. So let's say event A is randomly selecting someone for a clinical trial that is male. And event B is randomly selecting someone for a clinical trial that is female. Well, if you can only be female or male, and that has traditionally been the case, these two events are disjoint. Since a selected individual cannot be both male and female, and again, of course, this is, again, using that traditional binary expression for gender, then we would say that these events are disjoint. So that's one example. Here's another example. Let's say we're asked to determine whether events are mutually exclusive. Again, that's the same thing as disjoint. And event A is randomly selecting someone taking a statistics course, and event B is randomly selecting someone who is female. The question is it possible to find someone who is in both groups? Are there people that take statistics courses who happen to be female? I hope you said yes. I have female students in my class. So these events are not mutually exclusive. So that means the events are not disjoint. There can be an individual that's selected that's in both groups. There are women that take statistics. Here's another example. Let's say event A is rolling a number less than 3 on a die. So you roll a die. The sample space is outcomes 1, 2, 3, 4, 5, 6. So you've got 6 possibilities. Event A is rolling a number less than 3. Event B is rolling a 4 on a die. Now, one way that you could solve this problem is to think of all of the ways that you can roll a number less than 3 on a die, and then think of all of the ways that you can roll a 4 on a die, and then represent that by a Venn diagram. So here's a Venn diagram for this. And think of all the ways that you can roll a number less than 3 on a die. You could roll a 1 on a die. You could also roll a 2 on a die. So there are 2 ways to roll a number less than 3. And event A consists of rolling a 1 or rolling a 2. Event B consists of all of the ways that you can roll a 4 on a die. Well, there's only one way to do that. You just get a 4. Now there's no overlap between this set and this set. 1 and 2 lies entirely in A, 4 lies entirely in B. And since there's no overlap here, we would say that these two events are disjoint. Or we would say the events are mutually exclusive, which is exactly the same thing. Now here's another one. It says determine whether the events are mutually exclusive. This again requires some understanding or knowledge or background with decks of cards. Event A is choosing a jack from a deck of cards. Remember, there are 4 suits in a deck of cards: spades, clubs, diamonds, and hearts. And so if you're choosing a jack from a deck of cards, there are 4 ways to do it. You can select a jack of clubs, a jack of spades, a jack of hearts, or a jack of diamonds. And then event B is choosing a heart from a deck of cards. Well, there are 4 suits, so 1 in 4 cards in that deck of cards is a heart, or you could say 13 of the 52 cards are hearts, same thing. Now the question is, are those events mutually exclusive? Or alternatively, is it possible to choose a jack that's also a heart? And it absolutely is. A jack of hearts. It belongs to both sets. So we've got our jacks over here in event A, we've got all of our hearts over here in event B, and the jack of hearts lies in both. So these events are not disjoint because we can choose that jack of hearts. So we would say that choosing a jack and choosing a heart are not mutually exclusive events. Now, there are consequences for the addition rule. Remember, if the probability of A and B, or excuse me, if A and B are disjoint, then the probability of A being satisfied and B being satisfied at the same time is 0. Or in other words, the probability of A occurring and B occurring at the same time is 0. We don't have any elements in the overlap because there is no overlap. In that case, our addition rule becomes really simple. Now you just take the probability of A and you add the probability of B. So you can take all of the elements in this set, the count of elements in this set, and divide by the total number of outcomes. And then you can take the count of elements in this set and divide by the total number of outcomes and just add them together. And that's going to be the probability of A or B occurring. Now, typically, we also subtract the probability of A and B so that we don't count it twice, but there's nothing to count twice here because there was no overlap anyway. So this is the new addition rule, but it only works, for disjoint events or mutually exclusive events. If the events are not disjoint, we've got to use that traditional addition rule, which is represented by a formula, but it's also represented by this idea of counting all of the elements in A and B, but making sure to only count these ones in the middle once, and then dividing by the total number of possible outcomes. Okay, so let's apply this in an example. So it says, find the probability of A or B given the elements described below. A is rolling a number less than 3 on a die, and B is rolling 4 on a die. We've already looked at the Venn diagram for this. They're disjoint events. There are 2 ways to roll less than 3 on a die. You could roll a 1 or you could roll a 2. And there is 1 way to roll a 4 on a die. You roll a 4. That's it. That's the only possible way. So if I want the probability of rolling a number less than 3 or rolling a 4, I'll take the number of elements over here and I will add the number of elements over here. And then typically I would subtract those elements that belong to both sets, but there's nothing that belongs to both sets. So it just looks like I've got 3 outcomes here. That's the sum of these, 2 of these plus 1 of these. We've got 3 of those. And there are a total of 6 possible outcomes. So the probability of rolling a number less than 3 or rolling a 4 or both is just the probability of rolling a number less than 3 plus the probability of rolling a 4. And again, the sample space is 1, 2, 3, 4, 5, 6. So there are 6 elements in that sample space, 6 possible outcomes. So we just take the probability of rolling a number less than 3 and add that to the probability of rolling a 4. And typically we would also subtract the overlap, but there's no overlap, so there's nothing to subtract this time. So we just get 2 out of 6 plus 1 out of 6 is 3 out of 6, and 3 out of 6 reduces to 1/2. That's it for our discussion of disjoint and mutually exclusive events and the implications for the addition rule. I'll see you in the next video to discuss the rule of complementary events.